So what's a unit sample and what's a unit step? A unit sample, we're going to be generally representing as a delta n. Okay, and what this is saying is that it's 1 when n equals 0 and 0 when n is not equal to 0. All right, if we were to plot that out over time, all it's saying is that we're going to be 1 at n equals 0 and then 0 everywhere else. And life is good. Now, what's going to happen, though, whenever we do something like this? A unit sample that's delayed by one time step. So you're going to see this quite a bit. What does this mean? So now, everything is still the same. Like, this function definition is still valid. So when the thing inside of the brackets is 0, we have an output of 1. The function is defined as 1. When the thing inside the brackets is 0, we have a 1 coming out of this function. When the thing inside the brackets is not 0, we have 0. And so whenever we have an n minus 1, we have to think about, so at n equals 0, so whenever we're at 0, what's inside the brackets? It's a negative 1. And a negative 1 is not 0, so we have a 0 output. Whenever n equals 1, 1 minus 1 is 0, so now we have 0 inside the brackets. When the thing inside the brackets is 0, that means we have a 1 output. So we're going to have this. And when n equals 2, we have 2 minus 1, that's a 1. A 1 in our unit sample or our delta function is a 0 output. And it goes and goes and goes like this. Okay? And we can shift our unit samples however we want, right? If we were to scroll down and do another one. So let's say we have a delta of n minus 3. What do we think that would do? We were to plot that out over time. Right? And n equals 0, we have minus 3 in there, so that's a 0. At n equals 1, we have a negative 2 in there, that's a 0. At n equals 2, we have a negative 1 in there. At n equals 3, 3 minus 3 is 0. We have a 0 inside of our square bracket, so we have a 1 coming out. And then it zeros all the way down afterwards. Now, what's a unit step function? So this one is also brought in, and so unit step is usually represented like this, u of n, right? And what that's saying is it's 1 if n is greater than or equal to 0, and 0 otherwise. And so what would a plot of that look like? This function is going to look like this. When n is 0, that's a 1. When n is 1, it's a 1, on and on. Now, it's called a unit step because if we were to actually plot time steps before this, right, so negative 1, negative 2, negative 3, right, these are all negatives. They're less than 0. They're the otherwise category right here. And so this thing looks like a step, like on a stairway, right? You start at 0, then you go up to unity or unit or 1. That's why it's called a unit step. That's also why the unit sample is called a unit sample. It has an amplitude of 1 here, of 1 here, of 1 here. And the unit step, of course, is at 0, and then it has an amplitude of 1 starting at time step 0. And we can delay unit steps just like we can delay unit samples. So if we have u of n minus 2, for example, right, what do we think a plot of that's going to look like? It'll just be a unit step delayed by 2. But we can verify that, so we put our time steps down. If we go and look, so when n equals 0, 0 minus 2 gives us a negative 2 inside the brackets. That is the otherwise category here, so that's a 0. When n is 1, it's the same situation, negative 1 in the brackets. When n is 2, 2 minus 2 is 0, so that actually finally becomes a 1. And it goes on like this. And so we can see it's a delayed step. So by adding in that negative 2 in there, or negative whatever, right, we can delay a system. We could also, and you may say, well, what about if we plus something? And we can certainly do that. So if we scroll down here and we say, what is u of n plus 2, right? What would that be? So if we plot out our function, right, and this is n right here, and let's say this is 0 again, let's do negative 1, negative 2, negative 3, negative 4 over here, 1, 2, 3, and I know I'm not being consistent in my spacing. right? But now, what are those values going to be? So whenever n is 0, 2, so 2 is a 1, right? And actually all of these are going to be 1. Now what about, let's go back this way, right? So before it was basically we knew they were all zeros, but now there's actually some interesting business going on. Whenever n is negative 1, negative 1 plus 2 is still 1, so that's still a 1 output. When n is negative 2, negative 2 plus 2 is 0, so that's still a 1 output as well, right? These are the things inside the square brackets. And negative 3 plus 2 is negative 1, so now we're at 0. And so you can see in this situation, a plus has shifted to the left, right? So our unit step is still doing its unit step thing, right? Meanwhile, up here, an n minus 2 is actually shifting to the right. So a minus will shift to the right. It'll delay it in time. And a plus will shift it to the left. It'll advance it in time. And the same thing would go for delta functions. I'm not going to write one out here, but you could, for example, have a delta of n plus 3, for example, right? In which case that plus 3 has advanced the unit sample by 3 time steps. So instead of starting at, being its value of 1 at time step 0, it's going to be a value of 1 at time step negative 3. Now, how is a unit sample and a unit step related? If we think about it, if we have a signal coming in, right, and it is a unit sample, and so when n equals, let's say when it's 0, so this is our signal coming in, nothing, 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 it's a 1 at 0. Can we shove that signal into a system which will then produce a unit step? So this is our 0 point, so then it's 0, 0, 0, and then at 0, we're actually at 1. Is there a function we can put in here which actually would link these two together? What could do that? We need something to sort of, it's almost like we need a function or a difference equation which has the ability to remember that it's seen a 1. Because over here, for example, right, you're handing it 0 inputs, whatever, and it has a 0 output, so your function output is 0. And then over here, you're also handing it 0 outputs, but now your system is actually outputting a 1. Like, it's not doing the same thing for the same input. Do you know what I'm saying? It's different. There's almost like a state has changed. It's remembering something. And anytime you see a system which is acting differently at its output given the same inputs to sort of remember things. And so let's think about it. We kind of need a function. So let's say the output of our question mark box is y of n. And it's going to be some function of the input, okay? That sort of makes sense. So let's say it's going to be some function x of n, right? Now what we need it to do is while it's going through, as soon as the input goes to 1, the output goes to 1. So it'll probably be plus just x of n, if I could write my plus symbol correctly. But what else is missing here? What's happening at time step n equals 1 right here? Because at 1, it's going to be a 0 value, right? The input will be 0, but the output should stay 1. So we need a term right here that's going to be keeping it at 1. We can fix that with a y equals n minus 1. If we want a slightly more rigorous way of making sure like we can prove this to ourselves, we could also say, oh, the output of our function is going to be based off of some constant a1 times the previous output. And then let's just say plus b1 times the input. What we could do is come up with a table of values, just real quickly. We could say, okay, n is going to be 0, 1, 2, maybe 3. And fill in the values for y. Y of n, y of n minus 1, and then x of n. And what we can do is just fill in each value for the inputs and outputs. Now remember, our input is a unit sample, and our output is a unit step. So at time step 0, our output is a 1. Our previous output was a 0. Our current input is a 1. And then the next time step, our output is a 1 still. Our previous output is now a 1. And our input is a 0. And then this is going to stay like this forever. Now, this is a very simple situation, but what we can do with this is each one of these rows gives us an independent equation which we can use to analyze to extract information to figure out what A1 and B1 are. So if we take this first one at n equals 0 and plug in our values, we're going to say, oh, 1 equals A1 times 1 plus, times 0, because y of n minus 1 is 0, plus B1 times 1. So that's saying B1 equals 1. Then at the next time step, we could say still the output is 1 equals A1 times 1 plus B1 times 0. Now we know what B1 is at this point, but it doesn't. It's times 0, so it doesn't matter. And this is saying that A1 equals 1. And so together this is saying if we have a difference equation of y of n equals y of n minus 1 plus x of n, right? This thing, which we actually call an accumulator often, because it accumulates values, is a way to link a unit sample to a unit step. Similarly, could we come up with something that actually goes from unit step to unit sample? So let's say we have an input function, and it's a unit sample, right? And that's going to look like this. And then at 0, it jumps up to 1, right? Could we come up with something that you feed this into a box, and then out comes the unit sample? Right, and obviously there's the dotted lines too, if that helps you see them. Maybe it does. I'll put them in. So is there a difference equation which could do that for us? So let's just come up with a general difference equation. Now we want to solve for it. So we'll fill in our n values, and we'll put our different y values. Y of n minus 1, y of n minus 2, x of n minus 1. And then our n value 0, 1, 2, maybe 3. Let's do 4. Okay. So what is our input values? We can do those first, right? It's going to be basically 1, with the exception of this one. So at time step 0, our input is 1, and our previous input was 0, because it's a unit step we're giving it, and then it's going to be 1 for the rest of time, right? Because we're just providing it all of those things. Now our output, on the other hand, it's going to be 1 at time step 0, and 0 and 0, because there was no output here or here. And then it's going to be 0 when n equals 1, but the previous will have been here. And then it's going to move over 1 more, and it's going to disappear. I mean, well, it'll have gone to y equals n, y of n minus 3, but, you know. So one thing to take from this, too, is you can see a sort of shifting, right? So every time step, things move, right? We can even see some sort of evidence of this thing right here. Like this one is coming from this. And even like these zeros are coming from these zeros. All right, so what we need to do is then go in and use each one of these rows to come up with an independent equation, which we can then use to solve for our A1s and our Bs and stuff like that. So time step 0, our output 1 is going to equal A1 times 0 plus A2 times 0 plus B1 times 1 plus B2 times 1. Times 0. So these go away, and so we can conclude B1 must equal 1. And in fact, we can definitely conclude that even if we had more than 2 B's, right, because they'll all be 0. So we know this. Next part then is, at the next time step, our output is going to be 0. And that's going to equal A1 times 1 plus what? A2 times 0 plus B1 times 1. And we know B1 is 1, so we might as well just put it a 1 here. Plus B2, this time times 1. Okay, and this is saying then a1 plus b2 must equal -1. Then at the next time step, so this would be then, the first one was 0, this was 1, now let's go to time step 2. That's going to give us 0 equals a1 times 0 plus a2 times 1 plus 1 plus b2. And so what does that say? a2 plus b2 equals -1. Let's go on to the next one then. So it's going to be 0 equals a1 times 0 plus a2 times 0 plus 1 plus b2 times 1. And so this is saying what? b2 equals -1, which then is saying a2 and a1 are also 0. Okay? And so this is saying to convert a unit step into a unit sample, we need a difference equation in between, which looks like this. Okay, the 1 was right here, the -1 was right here. And what this thing is doing is really kind of taking the difference between two consecutive measurements. It's almost like an edge detector if you think about it, right? As soon as it sees a transition, so at this point, right, it's seeing, oh, there's something and there was previously nothing, so I'm going to have an output. But as soon as the value, the two previous values are the same, it's going to have a 0 again. This is actually very, very similar to a discrete time derivative too, which we'll be using later on.